had my, I just finished my 295 lab, and I had 3 people upstairs, 295.
Uh-huh.
And I had some people hang around after, and they asked me all kinds of questions. So we had a nice long discussion about quantum mechanics and everything for 295.
Really?
I was like, okay, well, I'm going to go to quantum now, so.
How did it evolve into quantum?
We started with like relativity and everything, and
So 295
things
is,
traveling faster than the speed of light, and
Oh,
why
okay.
that's not okay. And,
298 class, right?
Yeah.
295.
yeah.
That's quantum.
No, but they were asking questions. They
Okay.
stayed after
Are
class.
those students, the senior student in the old part, right?
No, they're
No, I
engineers.
think they, some of them.
Yeah, but it wasn't those guys out
530.
there. It wasn't them.
Oh, okay. I thought
Yeah,
that, okay.
we were up in the lab, and
Yeah, they were my other students, so
Mhm.
you teach them. So,
I mean, they just stayed after class and were
Uh-huh.
asking questions. So
okay, okay. All right, so I mean, I just almost have this, we have this addition and what is G value, right? And so now let's just summarize final. So there's a function. John, I can state this. G is L plus minus just sum of both derived CG coefficient last time spent almost all time in the class, so we can summarize. L minus plus n plus half. Okay, plus 1. L half. N half minus half. So when here, we have this the G value. Therefore, we have G either L plus half or L minus half or 2. For given G, we have n value between the minus G and G. Then this CG coefficient is a plus minus response to this plus minus. Therefore, L plus here, so that is a CG coefficient. That is L, S is half, right? And G is L plus minus half. And this one is M. ML is M plus half. And then this M2 is MS minus half. Yeah. This coefficient, this is the coefficient CL half L plus minus half. Now ML is M minus half. And M2 is half. We discussed these 2 types of CT coefficient last time. So now this is summary for all. This one, okay, maybe again, homework 2, homework 3, 2 equation, 2 problems you can use this formula. 7. One is L equal to 2, another L equal to 1. You can either use this one, use this formula, or the table which I gave you. So
Is that
for the
7.8?
coefficient here. Sorry?
Is that 7.8?
7.8 and 7.26. The first 2 problems actually similar. I mean the others you can how to find the L, G or something. But for the CG coefficient, you use this formula or you use the table. But just find what is L. I remember this case L is 2. This case L is 1. And S is half, right? So that this case always S is half. Then you just substitute L, M here for giving L, and then you have a G, so how much value of M. Or, of course, you need to determine the G and M, and then you go to either go to this formula or go to table to find each. So that is the homework. I think that's easy. You just practice. Okay, next one, I'm going to do one example, and this example also can help you to the third problem in homework 3, which is 7.27. So, it's an application. Let's consider a particle with spin equal to let's see if I need to spin here or not. Okay, but this also for journal. In central box. Central potential. And it's Hamiltonian. Is feeling as follows. So here, Hamiltonian of this particle, H hat. First part, we just in the spherical coordinate. Chapter 6, right? We have discussed 3 rings. Problem either in the Cartesian or in spherical coordinates. So we still, in terms of spherical coordinates, we have a radial part and angular part, right? So the radial part, if you remember, we have this radial kinetic energy operator. Suppose this mass is effect mass, or reduced mass, sorry, and the potential, which one is central potential. Now we have additional term. We are going to consider the orbital and spin coupling. So this term is, we have also angular part, which is also from the central force, and then the additional term is the spin orbital coupling here. So if you look, this term, the common, right, very common in our the chapter 6, we discussed this central potential like a hydrogen atom. So I'm going to rewrite this one by 2 parts. Here, H1 actually is nothing but the particle in this central potential formula, which is this term. Chapter 6. And H2 is coupling, orbital and spin coupling. Okay. So this is a simple addition of the 2. Now the question asks how to determine the eigenvalues and what is the eigenstate of this, right? So now we first need to find which orbitals are mutually commute each other, then we are going to find the joint eigenstates, right? So that is find first satisfy mutual commute orbitals. Let's first remember this one, H1. H1, in central we know that is commute with L square, right? H1, because this radial part commute with any angle that's independent of any angle, so that is we discussed a lot, right? So in this case, the commute with this one. And now, how about this S square? Because spin independent of any special radial angle, right? So that is also spin square, definitely is a commute. Okay. Then the addition of angular momentum G square actually is definitely is also commute, right? That is we have Gz. Because Gz equal to S Z plus Lz. And this one, H1 commute with Lz too, right? Remember chapter 6. H1 commute with L square and Lz. Then since spin independent of S1, so that H1, so that also commute with spin part, spin Z components and Lz, so add together is Gz. So that is, and then how about H2? Actually, H2 I cut, okay, H2 is also commute with the radial part, since H1 only is the radial part and angular momentum, and also G square, L square, sorry, H2 we need first, then we are going to analyze. So this is the H1, right? So H2, we can rewrite, since this is an inner product of the two operators, but we can rewrite, we know that is half of G square minus L square minus S square. We did this similar before. So then immediately we know that H2 actually is the combination or the function of G square, S square, Z square, S square. So definitely H2 commute with G square, L square, S square, and actually if we commute with G square, L square, and also the G, Z, and since H1 is only radial part and L square, so radial part commute with any angle, right? So that is H1. So those are all they usually commute each other. Then with this, so we have this finding, then we have the joint, and in states should have like this, right? So that if we consider this R and spin, this the eigenfunctions be the product of N, R, and L is only radial part, because radial part independent any angle. So the wave functions be product of, and now I'm going to write down here, Gm. Gm is the rotation, right? Angular part. Angular part. And this one is we can direct consider this, right? Because here the H1 includes this radial part. So you know this one is nothing but we know that is eigenstates is radial part multiplied L and L, right? Like hydrogen. So then here this one is addition of two. So I didn't have this one. I used the addition of total angular momentum here. But the radial part, same. So I keep radial part here, and the angular part is this total angular momentum, and this is addition of orbital L and S, right? So that something like here. That is the coupling. Okay, so now here. This be summation M, this one say ML, and MS, ML plus MS equal to M. And the Clapeyron coefficient, right? L, S, J, M, L, M, S, M. And then this all this linear combination of this L, S, M, L, M, S. And this here is this, since we consider S is half, right? So the G is always for between the L plus half and L minus half. Then this is actually this is G M, right? Oh, this is G. So I just read in just general. So this one, how much it is, we just found out. So that's just get general. Okay. Now once we have the joint eigenstates, then we can find the eigenvalue, right? So now Hamiltonian apply the states. Now let's see. Apply the states. So we give solving eigenvalue problem, right? I'm going to find this. And the left hand side is H1 plus H2. Now here that is I'm going to replace this eigenstates by the product of radial part and the angular part equal to Okay, so here I'm going to say E1 plus E2. And E1 is the eigenvalue corresponding to H1. So here, H1 R and L. And Gm is equal to E1 R and L Gm. Now, how much it is? H1 is the central potential. So we know it's a high symmetric, spherical symmetric, right? So that is nothing but En, right? For given N, independent of L, remember? And independent of any angular momentum part, right? So that's En is minus, like I have suppose suppose this is just electron. So electron Coulomb potential for here, which is mu e to the fourth power and 2h bar square n squared. Then from 1 to all the integer number. That is the first part. Then the second part, we just use H2, right? So H2, apply the states because that's the only angular part. So H2 apply RL, the radial part and angular part here, since that's equal to 0, right? Equal to E2 and L Gm. Now here, left hand side is half A, right? G square minus L square minus S square apply this. But does not affect on this radial part, only the angular part. So that's equal to here, J square apply this. You have a H bar square J plus 1, right? This one. And then L square is H bar L square L plus 1. And S bar square S plus 1. Then here is so this part is the part that is in and orbital angular momentum. There's a coupling. Then you can take the H bar outside. Here, since S is half, right? So this is 3 or 4. This is a E2. So that's equal to E2. And you can see here, E2 we have an index. E2 is depend on L and J. But L depends on N, right? So I'm going to say this is a depend on quantum number N, or given N, and L and J, right? But since S is fixed, so that is this one. Here, L equal to 0, 1. Go to N minus 1, and J is J L plus half L minus 1. So the total energy here, now I'm going to give an index N L J okay. So E the index is all right, that's enough. So the total energy is sum of these together, and one is dependent on only N is a high symmetry. When we have a orbital spin coupling, this reduces the symmetry. So this degeneracy also left. That is dependent on L and J. And of course, does not depend on M. We still have a degenerate, right? But given L and J, we still have 2J plus 1 degenerate. So this one can help you for the homework 3, problem 7, 27. That makes sense? Yes. So that case is kind of Hamiltonian, but no this term, right? There's some other, something like this, and you just try to make that as addition of these squares. Then that is the eigenstates, joint eigenstates, you can do that. Okay, I think that is, one more thing maybe I just mentioned. In case sometimes in the position representation, also just mention that is capture to the additional 3 elements. So here, in this spherical coordinate or representation and 2 by 2 matrix for spin. This is the for spatial. That's enough. So now here we have n, this one, right? N L G M. That is in general we use R N L or N L. That is equal to the two term, right? So here that is NL spatial part, and then the JM is L plus minus half M, right? And this one I just give you the equation. So now NL and this the inside of JM is we have the coefficient 2x1 and plus half. Okay, half minus half. So, did I remember here when we, for this term is L and S is half, then the ML is M plus half. MS is minus half, but now we have, right, this one is the optical angular momentum eigenvectors. And this one is spin, since the independent, right, to space, so we can write this one is equivalent to this. Remember we previously read this one. That is, this one is equivalent to this, right? But I separate the orbital part and the spin part. Since the orbital is in the spatial, so we can, when the position representation, we will write in terms of the spherical function, right? So now this is a term, first term and second one, which correspond to 0 minus n plus half 2 plus 1. Now here, L and M minus half is ML with a spin half. Here, this one is the same as L half, M minus half, this one. So that is, we use the Dirac notation. Now, this is Dirac notation. So in this position representation, we represent this the radial part and the angle, optical angular momentum in this position representation in terms of spherical coordinates. But spin part, we're going to have this 2 by 2 matrix, chapter 5, right? Remember? So this, yes?
Are you saying that these kets are just the same thing?
Same thing, yeah.
Okay.
Yeah, this one we write in terms of like J1, J2, M1, M2.
Yeah.
But actually, because they are independent, so we can write down in terms of product of two, right? So now I'm going to use this so I'm going to project to the position representation into a spherical coordinate. So that is this vector, right? drop. And, okay, N, L, and J, M. This one actually, they also, it is also product of radial part and the angular part. So this product of cat project to the spherical coordinates. So that one, we are going to, because this project become a function, right? So we use this capital psi, and the index is N, L. Then here, the J is L plus minus half, right? And M, that is index. And here, so that is R angle and spin. Spin here, actually I already include, so maybe plus minus, yeah. That is we're going to do. That is the function in the position representation for the spatial parameters, and for spin we use the matrix. So how to do that is now we are going to do this. So this one is R and L, which is radial part, right? This is only radial parts project to only R. And then the angular part, theta, phi, G, M. I can do this, right? Then we go further. Okay, so this one is still here. And this one inside, because this GM is two terms, right? So the inside is, let me keep this coefficient here. Now, this is a angular part, theta phi, and L n plus half. Now this is an orbital, right? And this one, now, when I say projection, so this one became a matrix, is minus half, right? So 0, 1. So this one is correspond to this. And minus plus, up here, coefficient, 0 plus minus m plus half, 0 plus 1. And here, say 1, 0, m minus half. And this one is half, is up, is spin up. So 1, 0. And now we can write further. So we know that this one is known as R and L function, radial function, right? And inside here, let's keep this coefficient here. This one is the harmonic, spherical harmonic, right? This is a orbital angular momentum project to the spherical coordinate. That is this one, right? Now the index L, okay, L is m plus half. Then function of atmosphere, right? And then here, 0, 1. Plus minus, 0 plus minus m plus half, 2 L plus 1. And this one is another spherical harmonic L, m minus half, 5. And this is 1, 0. So the wave function is like this. Or you just compare, because you multiply this one, you can see this is 0, only this one. This term is not. So finally, I can write this way. R and L, radial function. And I took this 2L plus 1 outside because it's common, right? So 2L plus 1. And inside, this one go to the second row. And this one go to the first row, right? So that is y L m minus half theta phi. Of course, we have a coefficient. This coefficient here, plus minus L plus minus m half. Half y L m minus half. And the second row is L minus plus m plus half y L m plus half. that is the final, in the position representation, how to represent the total wave function or any states of this particle, central potential with the orbital spin coupling. So that is the orbital spin couplings come from those, right? Yeah. Okay. Now we finished the discussion about addition to angular momenta. How about this add more, like 3 or more? So now we are going to analyze if we add more, how can we deal with those type of this addition, and give you some general technique or idea. Then you can extend to any addition, any 3, 4, 5 is angular momentum. That is last problem in homework 3. So addition of more than 2 angular momentum. How to deal with? Example, let's just consider 3. J is J1 plus J2 plus J3. How to deal with this? If we know how to deal with this, then plus J4, J5, we can do the same thing. So now let's look this. How to deal with 3? We know, we are already familiar with the additional 2. So we are going to use the idea from the additional 2 to extend our knowledge to here. So this one, I can rewrite in terms of J1 plus J2 first and plus J3. I'm going to say that's J12 plus J3. Okay, so or J1 plus J3 plus J2. So that's J13 plus J2 or J2 plus J1 and plus the addition of J2 with J3. So that's J1 plus J2, 3. So you can see here, this is addition of 2, right? This is addition of 2. Addition of 2 angular momentum. And if we write this one in terms of represented by another new one, then the additional 3 angular momentum became addition 2. So then we know the idea about this. We know we're familiar with these 2, right? So that is how to reduce. If we have more than 2 angular momenta, we try to reduce to additional 2 angular momenta. That is the way. Okay, so which way you are going to select? Either this way, it depends which one you prefer. And it also depends, for example, the homework, the last problem, homework 3. You are going to see the Hamiltonian, the behavior such that which is better for you to make this select which one, right? So now, okay, so just select one example and then we can go further. So now let's select, just an example, select J equal to J12 plus J3. Let's select this. So we are going to first add this J1, J2 together and J3. So in this case, right, how to determine, for example, how, let me first consider this, okay. Now, the first issue we need, this is, I think you asked me, J1, J2, the individual are commute each other. That is, otherwise we cannot. These are commute each other, right? Or mutually. It's commute mutually. First, so then we know that, let's consider addition this here first. If addition G, okay, I'm going to J1, 2 is J1 plus J2, right? That is the addition of 2. Square J1 square J2 square. Okay, I think let me do this one. This is okay. So now you consider so this J1 2 square. Okay, I can still write on here. We already know that. Okay. This they commute, right? So that's also mutually commute. Now, what do we because this is this one. Further, because this is a new the angular momentum we add together. This new also independent of S3 because this is independent, right? So that's independent. So that's S J1 2 square should commute with J3, right? Because J3 or J3 square because J1 2 is additional J1 2. So that commute is one. Then this is according to the addition of 2 angular momentum. If this commute with this one, this also commute with this two, right? So J square Jz. Do you agree? First, actually I don't need this term, but this term, so because they individually commute each other, right? So we know this additional is 2 also commute with this one because they are independent. So now you come to here, you consider this is an individual angular momentum, and this individual commute with J3, and we already proved addition of 2 individual is commute, right? So this is a commute. That makes sense? So this is a mutually commute. This mutually commute is we consider in this case in terms of a J1 2 plus J3. So this group is commute, and now you can. If you remember, if addition of these two, and this is enough. So this one and this one, for these two groups, we also have a J1 square, J2 square, J1z, J2z, right? They also commute each other since this one. That is for addition 2 angular momentum. We have 2 groups. Remember, we have one group is addition the total angular momentum, the square of total angular momentum commute with each individual square and also the J components for total. Then this each individual also commute. So we have 2 groups. Now come to here. This also we have 2 groups. One group is J1 2 J3. Another is J1 2 J3 and J1 2 Z component J3 component. So we have also J1 2 square, J3 square, J1 2 Z, That makes sense. Compare with this. Like here, we have this addition of the 2 and the total, and Z component total. So this is group 1. Group 2 is individual. Now this one is the total J square JZ, and each individual is J1 2 and J3. So J1 2 square J3 is individual with its individual components. Okay. So that is the key here. Then with these components, then you know this joint eigenstates. We are going to find a joint eigenstate for group 1. For this, for total, J2 square, J3 square, and JZ. This one is J12, J3, J and M, right? So given two individual angular momentum, the quantum number J12 and J3, then we have total J and M. Then for the second group, J12 square, J3 square, J12Z, J3Z. This one, we have a joint eigenstate is J12. In this case, I'm going to use J12, J3, M12, M3. So we have also same group like this. We have two groups for additional two angular momentum. Now additional three angular momenta, we first consider, first one is already addition, so consider new angular momentum. Then this became additional two angular momenta. Then we follow the same thing. There are also two groups. One group is total angular momentum square with each individual square and the components, they commute together, so they have a joint eigenstates. J1, first J12, J3, and J and M. Another is each individual, J12 square, J3 square, J12Z, and J3Z, they have this. So the connection between these two are the Clebsch-Gordan's coefficient, right? Let's first discuss how the allowed value of G and M. Then we go to this CG coefficient. So 3, let's consider what is allowed J and M values for given J1, J2, J3. Okay, let's consider this. So now first for J, right? We know J, so the maximum J value is here. This is additional J12 and J3. So that's be J12 plus J3, right? Not J1 plus J2. And the smaller equal to, so that minimum is the absolute value for J12 minus J3. But now be careful because J12 is changed. Also has not a fixed number, right? So, here, J12 is for given J, so that is J12 for given J1, J2 is within this. So what does mean? You first go to J12. For given J1, J2, so we have allowed J12, there are several values. Then for each J12, you come to here. So the J change, this is depend on J12. And J12 in this case is not one value, it is B here. So for given J1, J2, J3, you have to first look at J12, then you go to J. Then for given J, so when we have a J, we have an M value, right? So M value actually is, for each J, you will have M value. So how many groups? Depends on how many J12, and then you have how many groups for J, and for each given J, you have how many M. So that is help you to consider this the homework. I think that homework didn't ask you to calculate the CG coefficient. So this one help you to homework 3 in 732. That gives you 3 spin angular momenta, and the Hamiltonian is in terms of 3 spin angular momenta. And how to determine that? You need to find the joint eigenstates, and you need to find allowed total S, and this S12, whatever is 1, 2, or 1, 3, or 2, 3 is up to you. You can see, you need to think about the Hamiltonian. which way you select is better to represent the Hamiltonian. Okay, then the joint United States are numbers 4. So now the joint United States, this one, right? So we're going to do this. The joint United States is J12, J3, Jm. Here, the reason why, usually we just use Jm, right? Because that assumes J1, J2 is constant, we don't need. But here we have this one. Since J12 also change, so we need this index here. This one, I'm going to use this, as I did before, I insert an identity operator. And this we use the completeness of this eigenstates. So the summation for all, which one? M12 and M3. M12 plus M3 follow this selection rule, M. That is, when we select M, then we, for giving M, right? Then we are going to select all the summations M1 to M3 be satisfy this. Then this Clebsch-Gordon coefficient is, okay, so that is, we use the completeness of this eigenstates. So 3, M12, M3. We are going to expand in terms of this group, right? Because we are going to expand this giant eigenstate in terms of this. So that is here. This is about to be great for addition to same way, but the index here is slightly different, so we need careful. Okay, and this one is the Clebsch-Gordon coefficient of these states project to this one. So that's equal to summation M12, M3, M12 plus M3 is equal to N. Then now I'm going to use the index here, this Clebsch-Gordon coefficient J12, J3, J, M12, M3, N. And this is J12, J3, M12, M3. That's here. This one is another addition of two angular momentum, right? So here we need to write more. So now let me first keep this first summation, first group. You keep here J12, J3, J, M12, M3, M. Now here, this is the product J12, M12, J3, M3, right? Because the independent, so this eigenstate, this product is 2. One is in this space, which addition of J1, J2, another J3. So now this one, we need to write further. This one is addition of J1 plus J2, right? So we need use that knowledge to deal with this. Now I'm going to come here. Because J12, M12 is J1, J2, J12, M12, right? Remember this? And this is also addition corresponds to the addition of J12 equal to J1 plus J2. So that is addition of this joint eigenstate. That be, if I insert I, do the same thing. Then I'm going to remember this one is a group of M1, M2, and M1 plus M2 equal to M12 selection rule. That makes sense? So that is addition, since we first do the addition of J1, J2, then the J12 with J3. So this is a J12 with J3, we do this. Now we need to extend this one, since this is unknown. This is usually known, right? Because each integer. So this one we have to here. So that is J1, J2, M1, M2, G1, G2, M1, M2, and here. G1, G2, G, M1, 2, M1, 2. Then this is the Lebesgue coefficient for this additional G1, G2. M1, M2, M1 plus M2. So, sorry, equal to M1, 2. Then here is C, G1, G2, G1, 2, M1, M2, M1, 2. Then the state is G1, G2, M1, M2. So now, I'm going to substitute this into that. So finally, this is our initial state, right? Joint eigenstates of the summation of three angular momenta. So now, so here let me write again, J12, J3, Jm is equal to, now, first summation is M12 plus M3 and M12 plus M3 equal to M. That is Lebesgue coefficient C, J12, J3, J, M12, M3, M. Then the next summation here, M1, M2, M1 plus M2 equal to M12. C, J1, J2, J12, M1, M2, M12. And now here, this, okay, I think we have a summation I come out. That's it. Okay. Then here, this J1, J2, M1, so that is J1, M1, J2, M2, and this one, J3, M3. So now, for a single, each individual angular momentum, we know the eigenstates. Then for the summation of three angular momenta, we need to get this coefficient, two type of coefficient, and the product of each individual eigenstates. So those, you need to be careful when you do the homework. The last problem homework, you have three, right? So you carefully that spin S1 or M1 S and 2S, and then the addition of 1, 2. I suggest you just use table. You don't need to do use a table, and you get this one, but you keep all the summation, keep this one, so that's maybe several term, maybe only one term, depend on. And then for each one, each given M1, 2, you will have here. So that deal with the each term a little bit careful here. That is how to get a state. But I remember that problem didn't ask you to do this. Just ask you to get the eigenvalue of Hamiltonian. So, but if asked you to do that, you'll be careful here and here. Then with this, so any addition of J1 plus J2 plus J3 plus J4, for example, you can do first is J1, 2, 3 plus J4. And J1, 2, 3 is J1, 2, for example, J3. J1, 2 is J1 plus J4. So you just do the same thing until you, so here, when you have more, you first group all the remaining as one group and with another one. So that is addition to angular momenta. Then go to this group and again make this addition of two angular momenta. So group one by one, and then each individual you can add together. Finally, you can find something like this. Here you have if you have 1, 2, 3, you have to go to 1, 2 plus 3, like this became 1, 2, 3, 1, 2, right? And then the times total. Any question?
How did we make addition so hard?
Not too hard. Not too hard means I will not ask you to do more, but when in your practical do the research, at least you know the way, but I think a lot of people deal with that. There is some of a formula or some of regular, you just apply that result. But just give you idea. When we deal with this, how to treat this addition of more angular momentum. All right, so those are the topics in chapter 7. We finish now, actually from chapter 1 until here, or from chapter 3, I deal with the quantum system. We only deal with one particle, right? Even for this addition is one particle with a different angular momentum. So now we are going to go to deal with many particle system. That is more practical and realistic in the nature. So how to deal with the many particle, that is chapter 8 we are going to do. Even though the title is identical, but we are going to start from many particle. Identical particles system, right? So now we have, let's first consider the many, this particle may not identical, right? Many particle system. How to jump from a single particle, go to many particle systems. And what is the question we ask ourselves, different from the single? So there are several questions we're going to consider, and those questions we're going to discuss in chapter 8. First, okay. Those particles are identical. That's this one, right? Identical or not identical. What is different? Because identical and not identical is different. So we are going to first ask how to deal with the identical particles or not identical. Second one, those particles are distinguishable or not. Since we have many particles, then one is, even though they are identical, can we distinguish or not? If not identical, yes, we can distinguish. But if identical, can we distinguish or not? That is quantum mechanics idea, right? Number 3, those particles interact each other. Interact with each other or not, right? So that is very important. And in most cases, that is, for example, we deal with the condensed matter system, the many particle system. They interact, right? Coulomb interaction. But in which case we can approximately deal with the interaction very big or even not, or in which case we have taken into account how to deal with this. Number 4, that is when we have many particles, those come to our mind, right? Okay, the total wave function of the system. We are going to consider the symmetry. Symmetric or anti-symmetric. Now this symmetric and anti-symmetric in terms of exchange, in terms of interchange or exchange. We have many particles, so now I'm going to exchange. If only single particles, no such performance, right? So now I have many particles, in particular if they are identical, if I exchange I to J, J to I, what will happen? Does this wave function has a symmetry that does not change or change? And how to change? So that is another question. Then number 5, so what are their distribution, static distribution? this distribution means that now we have n particles, then you will see how the particle occupied energy levels depend on fermions, bosons, or classical. So those are also, when we deal with many particle system, we need to consider, right? Think about it in mind. Then after that, so we have introduced what is the Pauli is the exclusion principle, what is where the Pauli exclusion principle comes from, right? Exclusion principle. And then last one is explain this periodic table. Explain the periodic table. Why the periodic table is so nice to occupy all the elements have this own position in the table, water, underlying physics. Those are these topics we are going to describe in chapter 8. So now, let's first consider the many particle system, how to deal with the many particle system of Schrödinger equation of Hamiltonian. What is the information and what kind of problem we are going to solve about this.
Dr. Yu,
Yes.
does chapter 8 go into atomic bonding as well?
That is going to chapter 9. Chapter 8 only just consider symmetry or the permutation that the properties. And chapter 9, because that bonding we need the approximation. We cannot solve analytically like a heavy atom. So chapter 9 we are going to introduce this approximation method. Then you can deal with the bonding like variational property function or principle, that method we can, yeah. All right, so now first the Hamiltonian. Now the Hamiltonian is the kinetic energy, the operator plus potential, right? So now let's consider kinetic energy. Suppose we have n particle, so that one is simple, right? Okay, let me just immediately have this operator here in this position representation. That is the kinetic energy operator part, right? And plus, now the potential. I'm going to write here. Maybe depend on time, so let's just consider a very general case. So here, so this potential operator is complicated. That is answer this question. Those particles interact each other or not interact each other. So that is usually depend on this let's say external plus internal interaction. And then now external, usually you can find, like I'm going to say, external. We still can separate it, but internal here, it is complicated. We cannot separate. It is like Coulomb potential, this the interaction between R and RG, right? So that cannot be separated. So this part is difficult to come from. Here, like we have a particle in this external electric field or Mach field or gravitational field. Each one has its potential. So that we still can separate. But this one we cannot. So in general, we cannot write this Hamiltonian in terms of each individual. In general. If this term is not equal to 0, right? So, if yes, then we can write if there's no or ignore the interaction between particles, then we can write here each individual Hamiltonian single particle. That is the kinetic energy part. advance its potential, right? Then that we can deal with each individual single particle Hamiltonian solve the Schrodinger equation. Then all the summation of this energy is just summation of each individual. That is not described in this chapter 8, but just if we deal with this solved eigenvalue problem, we are going to deal with this. And in chapter 9, we consider some evolution. But here, in chapter 8, we in most cases also consider this. We are going to answer those questions. Right? So that is all right. That is Hamiltonian. Then the wave function. So now the wave function, I'm going to capital phi is R1 function of this position on time. That is this one, right? So that is the wave function of this many particle system. Then the Schrodinger equation. So we are going to solve the Schrodinger equation. I'm given Schrodinger equation, so that is this one, right? Partial psi. Time is equal to Hamiltonian. The Hamiltonian is a function of also the position. If the potential has a dependent on time, explicitly we also keep here. That is we are going to solve. But so in most cases we know the potential does not depend on time explicitly. So that means the partial Hamiltonian, also partial time, does not depend on explicitly. So we know that similar as we described in the single particle, the wave function can be separated in the product of a spatial part and time part, right? I'm going to use lower by here, only function of spatial variables and time only. These are same as we analyzed before, everything the same. The only difference now, this spatial wave function is a function of n positions. Right? So then this one, okay. Then we have a two equation. The Schrodinger equation is decoupled into the two. I just remind you we have did before for the single particle. This is P equal to P. Another is time independent Schrodinger equation. H Hamiltonian one. So now Hamiltonian does not depend on time, right? And the lower side one. And then the energy we are going to solve the time independent Schrodinger equation. Here, this solution is very simple. That is exponential minus square e t over h. Okay, that is very, very general. Just how to deal with this many particle system. We will solve, still we are going to solve the time independent Schrodinger equation, but this is for many particle, not for single. Then in general, as a wave function, we will have some information from there, how to calculate this probability, how to normalize this wave function, how to calculate the expectation value for many particle system. So probability. Basically, that is square of that is the square of the spatial function. Since we know this exponential square is 1, right? So that means when we want to see the probability is nothing but the function of the lower side. normalization. If we want to normalize the wave function, we have to go to the integral here. dr1 q, dr2 q, all the intervals we have two, drnq, and r1, rn, and t square, and that's equal to, as I said, the square is only special case, special part to the interval. Rn, q, over I. You do this to normalize equal to 1. And any function, any wave function we can expand in terms of this stationary. Okay, so any function here that is not eigenstate of this total manifold system, just any case. That is, we use the time transformation, this unitary operator. T naught, let's consider T naught equal to 0 case. And this one we already discussed before, so I just use in chapter 3, and I think we applied in chapter 4. So that is summation for n, coefficient Cn, and psi n r1, r n, exponential I e n, or h bar, t naught equal to 0. So Cn is coefficient is any wave function of t equal to 0 or t equal to t naught project to this is the eigenstate. Just first give you a minute, I'm going to explain. So here, set n is the eigenstate or vectors of the Hamiltonian, which we are going to solve here. The time minimum function, Schrödinger equation, when we solve this, we have allowed energy En and allowed eigenstate correspond to En. So here I have index n here, that is correspond to the eigenstates after solve, and En is allowed energy. Expectation value, any expectation value of any operator. States, right? So R1, R2, on, operator, stand, on, I say this is any states. If the eigenstates, we just replace by eigenstates. So here, since we know any wave function is extended in terms of this linear combination, so here you will see we have a 2 summation Cn prime, and then this expectation value of operator A between the eigenstates. Okay, and this one here. this is very general. When we deal with details, we substitute into details. Here, just give a general piece. I just use the knowledge we learned for the single particle and extend to the many particle system. When we want to deal with the many particle system, how to analyze the or obtain the probability, or how to extend this any function in terms of eigenstates or expectation value to this. Now, for consider spin, right? For particles with spin. So here we just consider this without spin, right? That's R. So we are going to define the variable as psi I is a group of position and spin. Then the Hamiltonian is in terms of not the R but psi 1, psi n, which kinetic energy part is still the same, right? That is G from 1 to n, so that part will not change. But the potential, if we consider potential, there's a term associated with interaction of spin, so you have this potential here is in terms of psi. And then with this, we solving the eigenvalue problem is again. So here, eigenvalue time element Schelling equation is we have to solve in terms of psi, not R. Psi 1, psi n, which is energy, which we are going to find if we solve this and then psi. That's time element Schelling equation. Example. Okay, just 2 minutes. Let's do one example. So start here. You can start this question next. Example. Example is multi-electron atom. Helium or any carbon, right? So those has more than 1 electron. Multi-electron atom. So in this case, let's consider first Hamiltonian. R1, we have Rn electrons. But now, let's consider this. So this is a capital R is the position of the nuclear. Suppose we have, and you have electron. Each electron have this position Ri, Rg, right? So the interaction between this electron with the nuclear field is positive is R, I or Rg minus capital R, right? So that is, we're going to introduce this one. Position of nuclear. But usually if we select position nuclear as 0 origin, then we ignore that. So that be the kinetic energy part, 1 to n, if we have n, Z, some atomic number, right? Z electrons, so this is a Z here. How many electrons? And then this kinetic energy part, electron, V, J square, and minus, if we consider nuclear, so we have the nuclear kinetic energy. Then plus induction. So induction here, I'm going to use R1, RZ, R1. The induction here, we have 2 terms. One is interaction between electron, another interaction between electron and the nuclear. So the negative part is Coulomb attraction, right? We have a negative. This is a Z. The nuclear has a ZE, right? ZE and the electron Z square and J minus R. J from 1 to Z. This is the interaction between the electron and the nuclear. and plus repulsive is electron, between electron and electron. This G, okay, I use G so this is an I not G, and this is a coulomb repulsive. You see, we cannot separate. So that is the potential here, potential energy for this complicated case. That how to deal with this, we have a lot of approximation. Okay, I think let me just stop it. This is just example show how this many particle system, then the wave function here you can see this wave function should be position and R. But of course, since this does not depend on time explicitly, so we drop time. When we solve this Schrodinger equation for Schrodinger equation for time independent this capital is time. Do you know the Gaussian code? That is deal with those interaction. We deal with from many electron or molecule or cluster. Those how to deal with this interaction. We have a lot of scheme here. So that is the example to show how what is a many particle system. Then from Monday we are going to deal with like identical, non-identical, distinguishable, non-distinguishable, multi-type symmetry, and we are going to construct the wave function. Before doing the details, at least we have some property of the function. So that is discussed. All right, I think the problem homework 3 now sound is not so difficult, right? Is that right? Yeah. Let me know if you have questions. If you can finish Wednesday, definitely I can grade and send back to your homework to your mailbox if you want to grade. If you think, oh, I can do Monday, that would be nice. I will grade it and just turn back to you on Wednesday. Then Wednesday I'm going to deliver the midterm exam. We will cover chapter 6 from the spherical coordinates and chapter 7, which we discussed the topic. The topic not discussed will not cover. And chapter 8, let's see how much we can do. Maybe it's construction of this wave function, I think at least we can cover. All right. Okay.
Thank you.
Thank you. So, really just go ahead and see if you have any questions. Just email. Yeah, I think this, the homework 3 is just do it. Yeah. The idea is we have not like a homework 2, there's a lot of issues to think about how to understand the question, how to answer the question. Okay.
It's starting to get hot.
Yeah.
Don't worry, it's going to cool down again tomorrow. Just a little bit. I think it's like 60 tomorrow.
Yeah, it's raining out, I think, tomorrow.
That's my favorite temperature.
60 is a solid temperature. 80 is a little unexpected today. Or
Today's 80?
78, I think,
Oh,
is
really?
supposed to be the high.
Oh.
Jacob,
Yeah.
Okay.
I went for 2 anime shirts in a row.
Oh, really? Oh, yeah. Oh, yeah, Tokyo Ghoul. Yeah.
Have you seen this one?
Uh-huh. They need to, I don't know. Did you watch the entire thing?
Oh yeah. But the
Yeah, I know.
the episode that will forever live in my head is the one where he kills Jason. You know, where he's being like tortured and then he breaks out.
Ah, yeah.
Oh dude, that was just like that was iconic.